Okay, let me share the screen. Okay, here goes.
Right, perfect.
Okay, you see that? Okay, very good. So now let me try to continue what actually I was discussing last time. And so actually we have discussed two special complexes. Okay, so what actually the complexes that I call superforms. Okay, and I'm going to denote them as a omega p/0, where p is just the form number and 0 is the picture number in this case. So actually we gave a local description of those forms, okay? And as I said last time, actually a form of this type can be decomposed in this way. So we have some coefficient in front, which are superfields, which depends on x and thetas, some dx's, okay, and some d thetas, okay. So the number of x's is r, the number of theta is s, and the total form number is r plus s, okay. Now, since actually I can add any number of d thetas as I like, since those objects are commuting quantities, okay, so therefore there is no upper bound to p, okay. However, I want to make now here another important statement, which is the following. Now, if I consider again a superspace which has n bosonic coordinates and m fermionic ones, then actually I have to remember that my coordinates are parameterized by xa and the fermionic coordinates by theta alpha. As I said last time, I don't refer to the fact that the alpha is a spinorial index. I just only counted the index as it is. However, when actually I make a transformation of coordinates, okay, suppose that I want to change the coordinates and then I want to write a new set of, coordinates, theta prime of alpha, okay, and then of course the new set of coordinates are expressed in terms of the old ones, okay, as a function of x and thetas, and also the theta prime alpha are expressed as functions of x and thetas, okay. So these are my reparameterizations, okay. And then if I actually if I check how the dx transforms, for example, if I check it how the dx transform, of course they transform covariantly in this way. Of course, I have the derivative of a of x prime, let's say, sorry, I would have to change the index b, and a plus d theta, sorry, here there's no prime, okay, theta beta d beta theta prime alpha, okay, and if I change the theta alpha into I get the dx b derivative of b of d theta prime alpha plus d theta beta d beta theta prime alpha, okay. So the matrix db x prime a d beta theta prime alpha db theta prime alpha and d beta theta prime alpha, this is our super Jacobian, okay, super Jacobian, which transform our differentials in these ways, okay. Of course, you see that this matrix is a super matrix, of course, because here there is some x functions which are bosonic functions taking derivative with respect to some bosonic coordinates, and the same is true also for the lower entries. Sorry.
That's a lot of thetas.
In the
Yes, thank you very much. Okay. Okay, so here this true. Wait.
That's wrong.
Wait. Yes, this one. Okay. So x prime a and then a theta prime. Thank you very much. Okay. So now this one is a bosonic function and I take a derivative with the fermionic coordinates. So therefore, this is just fermionic entries. This is a fermionic function taking derivative with respect to the bosonic coordinate, and therefore is again a fermionic expression. And then the last entries, this box here contains a fermionic function, and I'm taking derivative with fermionic directions, and therefore these are bosonic object. Of course, this is a block matrix, is a block matrix I can represent as A, B, C, D in this way. So, but it's a supermatrix. Okay. Now, this is important. Okay, so the reparametrizations in this case produce a Jacobian, which is a supermatrix, and naturally, the supermatrix in this way. So now, if I consider a form, okay, and then a P0 form, and then I'm going to write down all the indices now. So suppose that I have the index A1 to IAR, and then alpha 1 times to alpha S, and then I have XA1 dXAR, and then I have data alpha 1 up to d theta alpha S, okay? So now you immediately see that these objects appearing here, they transform covariantly, okay? They transform covariantly using the Jacobian, and therefore the indices appear in the functions here, they transform contravariantly, okay? So this means that this object here, this object that I'm writing here, it's a perfectly defined tensor, okay? Actually, it is a P0 tensor, which has a form number P and picture number 0. So what I want to say is the superforms can be discussed in terms of tensor, namely this object here, okay, transform correctly as a tensor, and then correspondingly the component of this form correspond transform contravariant. Okay. Now, what happened for? Okay, so this is a one sector. So the superforms are discussed really in the usual way. Those are tensor. I can use completely the tensorial algebra to deal with them. Okay, and the wedge product makes no difference. So you can take a wedge product among forms and it works perfectly. Okay, and also the differential, when I act with the differential on a P forms, that's, as I said last time, these give you a P plus 1 form, and the tensorial structure is perfectly maintained. What about the integral forms? Okay, now let's see what are the integral forms. Let me review what I said last time. So in integral forms, okay, which I call it P/M, okay, where now again P is the form number, M is just a picture, and in this case I'm consider just integral forms, so those forms which has a maximum number of pictures. And therefore, locally, I can rewrite this expression in this way. So I have some function here again. Now here I can put some power of the axis, and then I put all the possible power, all the possible deltas, okay? So I have M deltas, all the possible deltas along all directions. However, okay, here I can put just a number of axes as before, but then here I can act with derivatives, okay? So let me call it the B1 and the BS. So again, the expression B1, delta of B1 of the theta means just the derivative. Let me write down this way, which is clear probably. So it's just the B1 derivative of delta functions. Okay, and as we said the last time, they act by integration by parts. Okay.
Antonio,
Yes, please.
you also want the d thetas right there, right?
No, as I said last time, if I put a d theta here, suppose that I put a d theta
that's
here.
true. That's true.
Okay.
Yeah, and then you want the x to be p then, not r.
No, this is not necessary, because actually the P form, the P forms, actually it is what? It is just the sum of the axes, but then I have just the D minus the sum, I goes 1 to S of R, of BI, okay? So as I said last time, the derivative of delta function, they counts negatively.
That's true. Yes, yes.
So the total for number in this case, it is R. Okay. So of course you can take the maximal number of the axis, okay, that you can do it. But then you can also use the derivative to reduce the power, the form number of your integral form. Let's now consider a very special one, okay? A very special one. Let me consider that one, n/m, okay? And then this object is done in this way. Let's see how this works. Now, if I have the maximum number of d thetas, okay? So I have all d thetas here. Let me also put an index here, theta m, okay? And then I put all the x's, okay? And here I put all of them n, okay? And then here I have some function x, omega in front, okay? Now you see the following, that since I put all the possible d thetas here, I've saturated the picture number. If I put all the x's here, I saturated just the form number. And then you see, I don't have any other possibilities, because if I put the derivative here, then automatically, in order to set the p form into the maximal p forms, which is n in this case, certainly I have to add additional dx's, okay? And so therefore I cannot do it, because this is a saturated maximal number of dx's. Okay, this is essentially what is known as the top form in this case. So this is a top form, and then I want to tell you how this object transforms, okay? Let me put indices now, okay? Because I want to write down in a tensorial way, okay? If I put the indices, okay, what I can do? Well, one thing I can do is the following. This
sorry, Antonio, I'm very sorry. I was helping Marianne to get into the place, but so you put the top form. So I'm a bit confused, because you write P as R minus the summation of the BI, right?
Right. In this case, in this particular case,
yes.
So the deltas are just the naked deltas without any derivatives.
Okay.
So in this case, all BIs, so B1 equal to BS, oh, sorry, BM, okay? In this case are all zeros, okay? So then the total form is just n minus 0, which is just n.
I see. So you take the top form, okay.
Okay, then, okay, this is what is very important now is actually to discuss how this object is transformed, okay?
I'm confused with the notation. So even if you have derivatives upstairs, when you write PM, you still count M. Just the presence of one of them will count as one. It won't count more, just one.
Yeah, exactly, sure. Okay, the derivative doesn't change the number of the
doesn't change the number. Okay, thank you. I didn't get that. Okay.
Good. Now, actually, you see the following. Okay. Let me show you how this object is transformed. Okay. Now, to do it. Okay, I like to put indices here. Okay. Now, if I put the indexes, okay, I have the following. I have epsilon a1 up to an dx a1 dx. I will now discuss what is this, okay, object. And then here put also indices in this way. Epsilon alpha 1 up to alpha m, delta of d theta alpha 1 d theta alpha m. Let me now clarify this point, because this is a very delicate point, okay? You see, this object here, it is what? This is the Levi-Civita tensor, okay? And therefore here, when I write down this expression, essentially I write it in a covariant way, okay? Namely, I contract it in the index A's with the index A. So this object here, it is a kind of an invariant tensor. It is invariant under just a reparameterization of only x's, of course, because it transforms as a determinant, okay? So it transforms as a pseudo densities. Namely, if I make just a reparameterization of only x's, that will transform as a determinant of x's, determinant of the Jacobian, okay? Now, what about these terms? Now,
so,
this object...
excuse me, Antonio, as a mathematician, I'm not sure I know Levi-Civita tensor. So this is what, -1 to the sign of the permutation? Exactly,
yes, exactly.
Okay.
So this means it's a totally antisymmetric tensors, okay?
Okay.
Is 1 when actually I put like epsilon 1 to n, okay? And then if I make a permutation, I get the minus sign. And when actually two indices are equal, it gets 0.
Okay, and you do the same for the alphas?
now here the alpha is a little bit strange, because this object here, this object d theta alpha 1, this object is not a tensor, okay? So it will not transform as a tensor, okay? And so this object here, I write down in this kind of covariant fashion-like, but this object, I like to put it in order to keep track of the order, okay? So namely, what I can certainly write in this object, the delta 1, delta 2, blah, 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 up to d theta m, okay? And then, okay, the Levi-Civita tensor in front allows me to keep track of the orientations, okay? So if I change two of them, I get the minus signs, and then I want to keep this sign correctly, okay? So therefore, I can write down in any order that I like. The only matter is that the same order of this indices here appear as the same order here. It looks like as an invariant tensor, but it is not really properly tensor. It is just an order of the deltas, because I have to put it in order because the anti-commutes, so I have to define an order of them, and the epsilons in front keep track of this order. So namely, if I change two of the deltas, I can keep track of these changes by changing the indices of the epsilons, okay? Is still the Levi-Civita tensor in the alpha directions, in the alpha indices, okay? But it is not contracted let's say as the first factor, okay? I don't know if
Antonio, if I understand it correctly, what you're trying to say is that any transformation of coordinates will not induce the same transformation as for the dx on the delta d thetas. That's all, right?
Well, first of all, let's talk only about permutations, okay? Now, the equation that I wrote now, it is invariant under permutation. That's the first thing.
Yes.
Now I will show you how this transforms under change of coordinates, okay? Certainly, the bosonic...
Can I ask you a question? But
yes. I was asking a question also. Please.
The d theta should be even quantities, isn't it?
The d thetas, yes, the d thetas
are... of the exterior derivative and the grading of the theta.
Yeah, the d thetas are commuting quantities, yes, are even.
So the tensor in front should be symmetric.
No, because the delta function of d theta is in antisymmetric quantities. The delta function of d theta is anti-commuting, okay?
This is consistent then if you do calculation?
Absolutely, it is totally consistent, of course, yes. This is really the crucial point. The delta of d theta is an anti-commuting quantity. It's not a commuting one.
Okay. Okay, thank you.
Antonio?
Yes?
So under a linear transformation, the first terms with the dx change with the determinant of the linear transformation.
Sure, right.
Under a linear transformation of the thetas, the terms with epsilon alphas and the d thetas change as the determinant.
No.
It transforms as an inverse of determinant.
Yes.
This is the point. Let me show you this, okay? Okay, it is really the crucial...
because there are the deltas, because of the deltas. Sure,
exactly,
sure.
Exactly.
Yes,
okay.
because of the deltas.
Exactly. So you have to remember, essentially, then when actually you have a d theta alpha wedge d theta beta.
That's clear, that's clear.
Okay, and then when you transform this object, actually, it transforms like an inverse of determinant of the transformations. Okay, let's say J. Okay, d theta alpha. Yeah, this is a really the crucial point. Okay. Okay, now actually, usually when you deal with the real distributions, actually one has to put a modulus here, okay? You have to keep track of the sign, okay? However, in this present framework, we forget about this moduli, let's say the modulus, the absolute value of this object. We always forget that because we keep track of the orientations, okay? This really is a crucial point here, okay? Otherwise, you get you don't get the correct signs in all these steps.
But Antonio, you forgot the prime in that formula, right? Oh, they transform. Okay.
Yeah, exactly.
Transform. Okay.
However, let me do now a more general things. Now I want to make a really general transformation. Okay. So then I started from this expression. I make a general transformation. I got to the following: epsilon a1. Sorry, this formula is a little bit longer. So it is got just what? It's just a derivative. So let me write down dxb. Then I have d of b of x prime a plus d theta beta, derivative beta of x prime a. And then here I will have, okay, and also all the other terms here, okay, they will transform in the same way. Let me put it just once here in this way. Sorry, this is a little bit long. Okay, so it is n dbn x prime a n plus d theta beta n d beta n x a prime n. And then the same object, the same calculation I have to do for the delta. So I have epsilon, alpha 1, alpha m, and then I have a delta function of what? Well, here I have a dx. Let's say, let me put just another letters, c1, derivative of c1 of a theta prime alpha 1 plus d theta gamma 1, derivative with respect to gamma 1 of the theta prime alpha 1, and all the others in the same way.
Don't you want d theta beta 1, d beta 1 theta, right? Not x prime a. Am I right?
Where actually?
Second line.
Second line.
Am I confused?
No, it's, you see, this is just a dx bn, and then derivative with respect to the bn. So this means the derivative with respect to the coordinate x of x prime, and the d theta beta, and the derivative with respect to beta of x prime. So these are, let me finish, and then I will show you. Okay.
I am kind of surprised. I thought that the transformation would send even object to even, and there you send even to odd.
Of course, it is correct, because you see this object here, okay, this object, everything must be, okay, this object here, okay, everything must be anti-commuting, okay, because it's dx's, okay. So indeed, actually, this is a bosonic quantities, okay,
yes,
because dx is commuting, okay, anti-commuting. The derivative of x with respect to commuting variables is a commuting function. Then the other object is what? Well, the d theta are commuting quantities. But then I have taken a fermionic derivative of this. Okay, let me write down in this way. Let me finish just only to write down this, and then I will write for you in another way. Okay, let me just wait one second. Okay. Now, let me write down this in terms of the Jacobian, okay?
Yeah, I think it'll be clearer, yes.
Okay, the Jacobian is this way, dx b1, and then I have the Jacobian b1 alpha 1 plus d theta beta 1 j beta 1, sorry, this was not, this one was a1, whatever, a1, and then here a1, okay, times dx bn j an bn plus d theta bn j beta n an, and then the same is also works for the fermionic coordinates, alpha 1 alpha m. And sorry, I have to do one, sorry, I have to do one thing actually. I have to close 1 second my program, because actually it gets lower. 1 second.
No.
Un attimo. Okay, here comes. D theta beta 1 j beta 1 alpha 1 plus d, sorry, well, okay, it doesn't matter. dx b1 j b1 alpha 1 and all the rest again. So here there is a delta. Okay, now you see, now here I have the Jacobians. Okay, so this is just the block entries of the Jacobian, which is bosonic. Okay, so it's a bosonic quantities. This one is just one fermionic entries of my Jacobian. This one is again fermionic entries, okay, and this is just, so this is a bosonic entries, and this is just a fermionic entries. Let me remind you that my Jacobian, okay, has the following structures. Again, J, which has index A and B, J alpha and B, J A beta, and J alpha beta. So this one is a bosonic, this one is a bosonic, this one is a fermionic, and this one is a fermionic. Okay, so, and that actually, if you check how this transform, okay, they indeed transform bosonic quantities in bosonic quantities and fermionic ones in fermionic quantities. Okay. Now here comes the trick. Okay, now you see that the delta functions, okay, the delta functions, okay, what the delta function does? Well, the delta function means the following, okay, that the argument inside of delta functions, okay, should be 0, because the delta function tells you exactly that. It localizes where the argument is 0, okay? So this means that the d theta beta 1, for example, okay, j beta 1 alpha 1 plus dxb jb 1 1 alpha 1 must be equal to 0, okay? So therefore, I can solve this equation in this way.
No, wait, why is it? I was copying. Why is it true that? Why?
I have a delta function, okay? Delta function means what? Means that whatever is in front of delta function, okay, must be equal. So any function in front of delta function, it is like that if delta function of x is equal to 0, the function is evaluated at x equal to 0, okay? So the formula, okay, f of x of delta of x must be equal.
Yes.
Okay, this is just the distributional equations. Okay.
Yes.
This is the point. So therefore, everything which is in front of my functions, which multiply the delta functions, tells has to satisfy the condition given by the delta functions. Okay, and the condition given by delta function tells me that the d thetas are expressed in terms of the x's in this way.
No, but I am confused because delta function evaluates at 0, right?
Right.
So why this is equal to 0?
You see, the argument, let me show you. The argument of my delta function is this expression here. Okay?
Yes.
This is the argument of delta function. Okay?
Ah.
Okay. So the full argument must be equal to 0. Of course, there is another argument here. Okay. All the argument, okay, all the argument delta functions must be 0. Okay. So this means, you see, but inside of my expressions, okay, I have some deltas. I have some d thetas. Okay. So
no, but Antonio, I'm sorry, you have to go slow. I don't understand. So it is like you're taking, I'm confused. So I'm really very confused and I want to understand. So you say the argument of the delta function, why is it equal? I don't get why it is equal to 0. I'm sorry, I don't get it.
Okay. Let me do a very simple step. Okay. Suppose that I have a function. Okay. Let me do it in 1 dimensions. Okay. I have in one dimensions. Okay. So I have the following object. Okay. I have I have a delta functions. Okay. Of what? Of d thetas. And I have in front of this, I have a function of d thetas. Okay, suppose that I am just only the basic one. So the distributional equation means that I can replace this by say f0 of delta of d thetas. Okay, this is clear. Okay, because the delta function means that I have to set to d theta is equal to 0 any function which multiply delta function. This is just the distributional equations. Means what? That if f is a test function, if I integrate on d thetas, then automatically I evaluated the function at 0. This is just a sparse distributions. Okay? It's clear?
Okay, so here you should evaluate the function at 0.
Exactly. Now let me make another step. Suppose that I have this expression. F of d theta plus a function, let me call it a function a of d axis, okay? Suppose that I have a function of this, okay? Of course, this function a will be anti-commuting, okay? And then what happens? If I do the evaluation of this, I get f, where d theta is equal to 0, then this is evaluated at a equal to dx of delta d theta.
Yes.
Good. Now let's make another example. Suppose that I have a d theta plus b of dx's, and then a function of d theta plus a of dx's. Now, what I have to do? Well, first, let me compute where actually it vanishes. It vanishes when the d theta is equal to minus b dx's. Okay? So therefore, okay, again, by distributional equation, this means what? Delta of d theta plus b dx's, okay? And then I have to evaluate, I have to evaluate this function here using this equation, then I get what? Minus b dx's plus a dx, okay? Namely, I can rewrite this as delta of d theta plus b of dx's of f of a minus b of dx's, okay? Do you understand this example?
Yeah, sort of understand the example.
Good. Now let me do the last step. Suppose that I have an object like this. I have a function g. No, sorry, not a function, just a number. Okay. Let me call it this number chi, d theta plus b dx's. Okay. Time a function of d theta plus a dx's. Okay. Suppose again I have this expression. Now I have this function c in front. Okay. Now, since I have this function c in front, what is just a, sorry. Let me, so I want to make a different example. Oh, gosh. Oh.
Simone is here.
Suppose that I have, my c is just in front of this, okay, of d theta. Okay, suppose that I have the c in front of d theta, like, oh, I'm sorry. In this way, okay. Now, what is now the zeros of this? Is d theta plus b dx's is equal to 0. Okay, so then I have d theta is equal to minus 1 over c b dx. Okay.
Okay.
Now again, I use distribution equation. This means that I have a delta of c d theta plus b dx. Okay, time a function which is now what? Minus b over c dx plus a dx. Okay. So this, let's say this number, which is in front of the theta, I have to take care about this number because it appears here in the denominator, okay? Now, actually, we are almost at the end, okay? Suppose now I have the following. I still do the example in R11, okay? I have one coordinate axis, one coordinate d, dx and d theta. Okay, now let me write down the form now is 1-1 form, okay, which is now dx delta of d theta. Good. Okay, so what is my transformations? Okay, my transformation is dx of d theta under reparametrization transform in this way. Okay, let me call it jbb, jbf, jfb, a jff, or if you like, let me write down in this way, a, b, c, d. Okay, so this is a super matrix where these two entries are the bosonic entries, okay, and this one and this one are the fermionic entries. Okay, these are my Jacobian, okay, acting on the axis and the theta. Okay, so this means dx's transform into a dx plus b d theta, and the d theta transforms into c dx plus d d theta. Now let's see how this function here, omega 1, 1, transforms. Okay, it transforms in a dx plus b d theta times delta of c dx.
Sí, dime.
¿Puedes hablar?
Sí, sí puedo.
Ah, vale. Oye, salgo ahora del cole.
Mariana.
He visto los mensajes, están en la playa, ¿no?
Okay.
Just a moment, I stop Marianne.
Okay.
No, wait.
Okay, I did it, go.
Okay, very good. Now actually look at this expression. Okay, now I use actually the trick that I was mentioning before. Okay, so if I use the trick that I mentioned before, actually I have to do the calculations. Okay, now if I do the calculation, it happens the following. Okay, so first of all, I have to check what is my zeros of my deltas. Okay, so this means d of d theta plus C of dx is equal to 0. Okay, so this means d theta is equal to minus C over d of dx. Then I use this equation here, okay, and then I got to the following. So I get A dx minus C over d b of dx. Oh, sorry, I made a stupid mistake. Okay, I have a b of C over d dx delta of C dx plus d of d theta. Okay, now you see what happened. Let me now rewrite this expression. Okay, this expression, this is what? It is A d minus b c over d. Okay, of dx times of c dx plus d of d theta. Okay.
Yes.
We are not there. Still, we are not yet there. Okay. Okay. Let me rewrite these expressions. Okay. Now you see that this expression here. Let me first write down the overall factor dx. Okay. Now you see this is the delta function. Since it's a delta function, I can expand these delta functions around this expression. Okay. So I can expand this delta function in this way. So I have d thetas, let me write down in this way, plus d minus 1 of dx. Okay. Now, actually, first of all, I want to remove this d, okay? And then for that, I use just the property of a delta function. So I have ad minus bc over d. So I remove this object, I get 1 over d in front because it's a delta function. And then I have a delta of d theta plus d minus 1 dx. Last step, you see, then I expand this object in a Taylor expansion. I expand around d theta is equal to 0. Then the first term of expansion is plus d minus 1 dx, and then a derivative of delta functions. I do a Taylor expansion of this, okay? Then my Taylor expansion stops because the dx wedge dx is equal to 0, okay? So therefore my expansion stops there, okay? Then let me first write down, so I have ad minus bc over d squared, then I have a dx, then I have a delta of d theta plus d minus 1 dx delta prime of d thetas. Okay, that's it. But now you see what happened. This object here, dx, it collides against the dx again. Okay, and so therefore these terms drops out, give you 0. So the total answer, it is what? It is ad minus bc over d square and the dx of delta of d theta. But this object is what? It is just the superdeterminant of abcd of dx delta of d theta. Okay, it gives exactly on your nose the superdeterminant of the Jacobian transformations. Okay, so all these things tells you that the top
question.
Yes.
So this step where you turn d into 1 over d, I'm taking it outside the delta function. If this were an honest delta function from real analysis, that should be the absolute value of d.
Sure. I agree with you exactly. Okay. Sure. Indeed, these are not really honest delta functions. Are actually what are known as de Rham current. So you have to keep track. Okay. So let's say this is the correct mathematical.
Did you say de Rham current or direct current?
De Rham
current. Okay.
Yes.
Good, thanks. So
they are not really the Dirac delta functions, but there are these objects here. So you keep track of this. Okay, sure. No. Of course, if you put absolute value, nothing works. Okay, because automatically you don't get the correct sign and whatever. Sure. Very good. So in this way, automatically you get your superdeterminant. Now, if you're brave, actually, and if you do it the same calculations using the general form that I write down here, then always get the superdeterminant of the Jacobian, okay? So my form, my top form, omega n/m, transform as the superdeterminant of the Jacobian transformations, omega n/m. Okay, so therefore, this tells me that indeed this object transform as as a section of the Berezinian bundle in this way. Okay, and I'm happy about this object. So this is the object that I like to define as a volume form, because this actually transform correctly as the volume of my supermanifold. Okay, so Rita, well, actually we talk about integration measure on some supermanifold, which is a supersphere or super CP or whatever. It is obtained exactly like this. If you construct your this top form, okay, suppose that you want to do it for a supergroup, okay? You want to do for a supergroup. Now, if you want to do it for a supergroup, suppose that the G is just the map which map some coordinates into a supergroup, okay? So it takes some coordinates. For example, you take the exponential map of I, well, without the I don't care about the i's, okay? I have like some bosonic generator T of A. I have the coordinate XA.
No, but do the Morer-Cartan, that I need that.
Yes, yes, I will do it, okay? Q alpha and theta alpha. Suppose that I write down the group element in this way, okay, where x's and theta are my coordinates, okay, and TA and Q alpha are the generator of my superalgebra, okay. So therefore, generator superalgebra means what? Q alpha anticommutator with Q beta is equal to some structure constants, alpha beta A TA, and Q alpha and T of A gives some F. This is the commutator, alpha A beta Q beta, and then finally I have a TA, TB, and then here I have F, A, B, C, TC, okay? So this is just my, let's say, my generic superalgebra. So therefore I can construct the Morer-Cartan forms in this way, G minus 1 dG, okay? So I take the differential of G, taking differential of G, of course, it means what? It is a G minus 1, taking the differential, which is a TA, D of XA, then the QR anti-commuting, so I have to keep track of my signs in this way, alpha, and then I have a G. Now, of course, what I have to do, I have to use the Baker-Hausdorff for Campbell formula in order to bring this object on the other side. If you do the calculation, you end up with something like that. I have some generators, okay? And then here, I have to write down my Morer-Cartan forms, okay? Q alpha and A alpha. Okay, of course, this object EA and E alpha are complicated expression. Of course, that will start in this way, but then I have some complex structure like alpha beta, theta alpha, d theta beta, and so on. Okay, I have all the other terms, and of course, E alpha will start with d theta alpha, and of course, I have also.
No, but Antonio, I have to understand what you're doing. So you write the G as the exponential of, so your XA and theta alpha are generic coordinates, right?
That's right, that's right. These are the generic coordinates on your group manifold, yes.
Yeah, but why then, I don't understand, there is a gamma alpha dXA minus Q alpha dX alpha, where is this coming from? What are you doing? I don't get what you're doing, I'm sorry.
Where you are lost? Okay, when I calculated the G minus 1 dG,
yes, where is this coming from?
Well, this object here, okay, this object here, it is what is known as the Morer-Cartan forms.
Yes.
Okay? So the Morer-Cartan forms, okay. So you know that this object, it is an element of the algebra, okay? It is an element of the Lie superalgebra, okay? And there are four, okay, it satisfies the Morer-Cartan equation. In fact, if you calculate the differential of G minus 1 dG, this gives you minus G minus 1 dG wedge G minus 1 dG, okay? So it satisfies automatically the Morer-Cartan forms, okay? So since it satisfies the Morer-Cartan forms, you know that this object is an element of the algebra. So if this object is an element of the algebra, you can express in terms of the generator of the algebra, okay? So this means my Morer-Cartan form, it is written as a decomposition along the generators of my Lie superalgebra, okay?
Okay.
Now, Please notice that this object is one form, so it's non-commuting quantities. Now,
Yes.
this object is one form because the TA are bosonic generators and EA are fermionic quantities, because those are.
No, but I still don't understand that formula.
Which one?
Probably it is something very simple. So you're like a G minus 1, and then you write that expression.
Well, this expression.
No, upstairs, up.
Which one? This one?
Yeah.
This one? Okay, so, but how you calculate this object? Okay, so I have a G, which is just the exponential.
Oh, you are explaining that. Okay.
So this is just an exponential of AXA plus Q alpha of theta alpha. This is my group element, okay?
Yes.
So it maps the group manifold into the element of the group. Okay?
Yes.
Then I calculated the differential of this.
Yes.
If I calculate the differential of this, I get it TA dxa. Please notice that it is anti-commuting, so I have to take a minus sign here, and then it gives you my G. Okay, I take just the differential of an exponential, and then I have to apply G minus 1 dg to this expression. Of course, this is not easy calculation. I'm not saying that it is easy, okay? It is cumbersome. You have to do a little bit of work. You have to bring this object on the other side in such a way that the G minus 1 G is equal to 1, okay? But when actually you bring on the other side, you have to do all the commutation relations. You have to use the Baker-Hausdorff-Campbell formula to do that, okay? And once you use the Baker-Hausdorff-Campbell to do this object, then automatically you get something TA with some object here, and then Q alpha and some quantity here, E alpha here. Is it clear now?
Let's say that I sort of see how you derive it, but the word clear I wouldn't use.
Okay. All right. So
what I mean, the Baker-Campbell-Hausdorff, first of all, it's for a group, a Lie group, and not for a super group.
It works. It works perfectly, and also for a Lie superalgebra.
No, but the exponential map for a Lie supergroup, it's a mess, it's terrible thing, right?
What does it mean, terrible? You can do the calculation as in the usual case.
Okay.
Well, it is not terrible at all, because actually, if you expand the thetas or you expand the q's, it actually gives you a polynomial. It is not even terrible. It is a simpler than the usual. Let's say the complicated part is just the normal group. Okay, that of course is a complicated object, but the other part, namely the fermionic part, is just a polynomial expansions.
No, I agree. The problem I have also for the group part. So will you tell me where I read this derivation in the ordinary case?
Where?
Yes.
Well, Kobayashi no Mitsu, I think, or
yes.
Any book about Lie groups. I mean,
no, for example, in Varadarajan, there is no such a derivation.
Well, okay. Any serious book on Lie groups, okay, you can certainly find it. Take Gilmour, Lie algebras, Lie groups, and applications, okay, for example, or whatever, Naimark Stern, for example. That's
fine. You will not find it in NAP, which I know by heart. It will not be there, but Kobayashi no Mizu, thank you. And the other one?
Gilmour, Lie groups, Lie algebra, and their applications, okay.
Gilmour, fine.
Or, for example, there is also the book by, I think, Coxector. I think also, also on Frappat, Sciarrino, and Sorba. This Lie algebra.
No, but I want it for the the ordinary.
For the I think that in the Frappat book there is both ordinary and Lie superalgebras.
Okay, maybe.
I must say that just for just for like the differential geometry of the Moyer-Cartan form, I also like Isham's book.
Which one?
Yeah, exactly.
Isham's book, Differential Geometry for Physicists.
For example, yes.
The guy?
Chris Isham, Isham.
Isham,
okay,
yeah.
Fine.
This book actually is a perfectly, yeah.
Thank you. There
So
is no
actually-
such a thing. Alas, for mathematicians, they don't compute it. Okay.
Well, okay. Well, okay. I learned it in a group, in a class, in mathematical physics class at the mathematical department in Genova. Okay, I learned it from a mathematician. Okay.
Okay, fine. Probably not the ones that go around the math department in anywhere outside there. Okay. No, I'm happy. You gave me reference. I will look.
Okay, so when you use this formula, okay, then automatically you can compute this object here. Let's say you can call this object, let's say frames or a Marocartan forms, so as you wish. Okay, and where I'm now. Okay. Yes. Okay. Sorry. If you have now a group, for example, or a super group, then you can calculate this object here. And then the top form, okay, where n is the number of the bosonic generators, and m is the number of fermionic generators, then automatically my forms will be A1 wedge. Oh, sorry, let's put it different, otherwise you don't understand. So I have A1, AN, A1, AN, and then I have, sorry, I put in the other line, epsilon alpha 1, alpha m, delta of A alpha 1, delta of A alpha m. Okay, so that's actually is my top form, okay, for a group manifold, okay, and then if I make it explicitly, I will have the Beretzinian of my Jacobian times the x's, all the possible dx's, and the possible d thetas. Okay, and this is just the volume form, okay, or if you like, is just the volume factor that you have to insert in your integral. Of course, when you do the integral of this object, okay, so when you do the integral of this object, omega n of m, okay, you have to remember that you have to integrate of the x's, you have integrated on d thetas, you have to integrate on d of the x's, and then you have to integrate it on d of d thetas. Okay. Then, of course, the first, this integral is easy because this just remove the axis. Okay.
So now you are computing the volume for the group, right?
Exactly. This is the volume for a supergroup. Okay. The volume for supergroup. Okay. The integration on the axis is very easy because you have to take out the top form. Actually, take out the top form means erasing this part. Okay, so the final answer is just the integral of the Beretzin of the Jacobian transformations, and this is the integral of dx's and d thetas.
Okay, so when you write the j, so this j is the transformation, the sense.
Right. Okay, the transformation. Okay, this object EA, which I wrote before, okay, that you calculate for the Marer-Cartan equations, okay, this is expressed in this way. It is just dxb, then I have a, let me write down in this way, jba plus d theta beta, j beta a, e alpha, it is what? dxb, jb alpha times
right.
g beta alpha.
Yeah.
Okay. So here in my supermatrix, of course, this object here is a supermatrix, is a BA, beta A, JB alpha, AJ beta alpha. Okay. And of course, it's a function of x and thetas. All these components are with function of x and thetas. So the final answer is just the integral of the Beretzinian of this object here, JBA, J beta alpha, JB alpha, and J beta alpha, integrated on the variable x's and d thetas. And that gives me the volume of my supergroup, whatever, I mean, SU n slash n, n prime, whatever. Okay, that gives me the volume of my supergroup. Of course, you have to calculate this expression. You have to calculate this object here. That's, I mean, that is your, you have to do it. I mean, there is no way to to compute the volume of the group without computing this object, of course. Okay.
Yeah.
It could be very complicated. I mean, it could be very complicated. Well, for classical groups, for classical supergroups, there are formulas. I mean, now, so we know explicitly those formulas. I mean, we know it. Okay, so it's not a difficult task. Okay. Now, of course, what actually you can do also, okay, if you have a top form n plus m, okay, certainly you can multiply by this object by a scalar superfields, okay, and of course you are still having a top form, okay. This object will certainly is a top form again, okay, and if this is a scalar, so it is an invariant superfields, then this object will transform again a Berezzinian object. Okay, so it's a section of the Berezzinian bundle. Okay, so therefore, if I want to integrate this object, I will have to integrate of x and thetas and omega n slash m, and that's I have to integrate of d axis, d theta, of d axis, and d of d thetas, and then finally I get the integral of the phi of x and theta times the Berezzin of my transformation j. That gives me just an integral which is reparametrization, super reparametrization invariant integral. Okay, so this means just a number. Okay.
So I don't. So there is something that disturbs me.
You still want to put like the brackets dx d theta in that last expression, right? Is that?
Well, these brackets here, okay. It is just a symbol, which means just the integration on the Berezzinian bundle, okay? So on the full Berezzinian bundle, okay? Of course, this is in invariant quantities, okay?
What do you mean invariant quantity?
Which does not transform. I think it's invariant. I mean, I don't like this object. I don't like to discuss about this point. Okay, but let me discuss.
No, but it's important.
No,
wait.
No, it is not important.
No. There is something which is important, which I like to understand. So sometimes you write dx d theta, d dx, d d theta. Sometimes you don't.
Well, it depends on a situation. If I have to integrate on x and theta, okay, the integration, the Berezzin integral, okay, Berezzin integral of a function of x and thetas, okay, either I write it in this way, or if you want to list all the variables, I write it in dx and d thetas, okay? Okay. If I want to integrate it on my tangent bundle, okay, my tangent bundle being pi t of Sm, okay, of my supermanifold, I have a what? Well, I have something which is fx theta, dx, and d thetas. So I'm going to integrate it on all the possible variables.
Okay.
Okay. So for me, this is just a way to list those variables. Okay.
No, I understand. So if you have a function, you use the usual Berezzin integral. If you have a form, you go to the bundle.
Exactly. Right? But pay attention that if you want to write down an integral which is indeed invariant, okay, then you have to integrate a top form. What is a top form? Something which is transformed in the Berezzinian bundle, okay?
No, of course.
And then exactly what I say. So it is like, okay, so when you actually write down an integral of a form, okay, and here I have an integral on a top form, which is just this one. So an integral on an integral forms in this way.
No, thank you. It is important, the difference, this. Okay. Right.
Okay. Are the volumes of the simple supergroups all known?
Yeah. The supergroups like UN/M or OSP are known. Yes, true. Yes.
Who worked those out? Where are they worked out?
Well, there are several works, some very old works, but actually the most recent one, actually, it is a nice paper done by Zhang and how is the name?
Coulombier. I would not use the word nice for what they write.
Okay, there is also, for example, there is also a paper by Voronov where actually calculates some volumes of some supergroups, superspheres, and these things. And So in a paper with Roberto, for example, and Leonardo Castellani, we write down the volume for some Kähler manifold, for example. There is a nice way to rewrite this in terms of the Kähler forms and whatever. Okay, so there are explicit formula. Indeed, actually, for all classical supergroups like SUN/M or SPN/M, there is an explicit parameterization of the Maurer-Cartan forms. Then actually you can do the calculation. It turns out that some volume of some supergroups are zero. Okay, some volume of some supergroups are divergent. Okay, some volume of supergroups are finite. Okay, so it depends. Okay, there are with respect to the, let's say, okay, some of them could be divergent because it's just a non-compact part of the group which diverges. But it turns out that even if a non-compact part of the supergroups, the fermionic coordinates are so powerful that it put the volume to zero. Okay, so you have to, let's say, to play a little bit. Okay.
So I tell you what I don't like in Coulombier. Okay, somehow he says that OSP has a compact form, but it does not. So I'm not really sure what he's saying.
Well, the volume in this case will have certainly a non-compact part due to the SP part, of course. Yeah.
Yeah, that you say, of course, but they happily integrate on that part, claiming that, well, I'm not sure what they write because they write SP and that they integrate happily. So
well, happily, okay. When you perform an integration of supergroups, you have to take care about something, okay? That, as I said before, okay, it happens the following. When integrated on the X coordinates, so the bosonic coordinates, the integral could be divergent, okay? Then you understand it is non-compact part, okay? However, you integrate also on the fermionic coordinates, okay? When actually you integrate on the fermionic coordinates, it tells you that, okay, well, you have to do a Berezin integral. Berezin integral means you take some derivative. It turns out that in some cases, okay, these two things conspires to give either zero, okay, if the thetas win, or even finite part. Let me show a very simple example, okay?
Suppose yes, I need to see an example because Coulombier, I don't understand.
Okay, suppose that I want to do integration on R1, okay? Suppose that I want to do such an integration, okay? Okay, good. So let me think.
So are you viewing it as a group?
No, sorry, one second. Okay. Right. Okay. Suppose that I want to do integration of this type. Okay. So what I have to do? Well, what I want to integrate is something like that. Okay, one form. Okay. So this object is what? Is a function of x and thetas. Okay, and dx delta of the thetas. Okay. Now you see the following. Okay. So when I integrated these expressions, okay, when I integrated these expressions means that if I do the integral of x and thetas, dx of delta d thetas, okay, so this means I have to do the Berezin integral of x and thetas, okay. Let me now put here dx's and d thetas, which means just the Berezin integral. So this is my integral of my top form, but then I'm left to the integral of the Berezin integral. Berezin integral means what? It's just a derivative with respect to theta of my functions of x and theta, computed at theta equal to 0. And then finally, I take just the Riemann-Lebesgue integral of that. Okay. Now, let me try to. Now, certainly it could happen that this expression is a constant, okay? This expression is a constant, okay? So suppose that I have a function like x and thetas, okay? And my function is this type, f0 plus f1 of thetas. Certainly, this integral will certainly diverge. If f0 and f1 are constant, when I integrate over the x's, give you something which is divergent, okay? Because if you do the calculations, okay, if you do the calculation, you get
well, it depends on what it is, f1, right? You know, f1 could be a nice function. Yeah.
Yeah, sure, but it could be a constant also, okay? If this is constant, of course, this is just f1 and thetas. Sorry, they take a derivative, I get f1. okay, time the axis, and of course this diverges, okay. But suppose that my function fx and theta is just f0, any function of f0, okay, so it doesn't depend on theta, okay. Then if I take a derivative of these functions with respect to the theta, I get a what? I get 0. Okay, so you see that in this case, okay, even if my functions f0 if f0 of x could be any functions, okay, I can still do the integral, okay. So this means that when you take some derivative, so when you calculate some Berezin integral, it could happen that the derivative with respect to the thetas, okay, automatically put to 0 some integrals, okay. It could also happen that there is a conspiration between the thetas and the x's in such a way that the 0 and divergent part, indeed, they cancel out. I can show you that, but I don't know, it takes me like half an hour to explain how to do it, okay. So there is a way to regularize, there is a way to regularize between the fermionic coordinates and the bosonic coordinates in such a way the integral is 0, okay. So you have to be careful. I mean, when sometimes, even though the part of the group is non-compact, you can have a derivative with respect to the theta in such a way that the final integral could be 0 or could be finite.
No, but Antonio, in this case, it seems to me that is very intuitive that this must be 0 because it's like a Stokes theorem, right? You're not looking at the top object.
No. Well, Stokes theorems, well, okay, if this object is if this object is f naught of x,
yes.
Well, it could be a Stokes theorems, okay.
Yeah, I mean, you're not looking at you know, something which is a top object, so of course you get 0. So it's not so.
No, not in this sense. Of course, this is not in this sense. Not the Stokes theorems in the form language. This is not true, okay. It is a sense that the top component of my superfield is 0. It doesn't make it. Okay, I can do it. No, I don't want to tell you that. Okay, I just only to tell you that it is not the Stokes theorems. Okay. It just tells you that the volume form that you get, so the volume factor that you get, when you expand in the data, could be 0 because there is a no top form. There is a no top.
I am aware. I am very aware of it. Yes.
Right. So this means that it could happen 3 cases. Either your integral is divergent because the non-compact part of the groups actually makes a divergent integral. Or you get 0 because the Berezin derivative, the Berezin integral takes this to 0, or you can conspire the 2 things, okay? There is some cases when the integral of x's and the integral of thetas gives you a regularization, and then you get a finite integral.
Yes, yes.
Okay, so what is written on Zahn-Coulombier, it is not wrong. It is a very deep question, when actually you can perform such a regularization. This regularization turns out to be just a definition of picture change operators, if you like. But then I think that
may I rephrase, if I understand this correctly, that the integration of f0 and f1 will not tell you anything about the integration or f. I mean, it's not transparent, then f is integrable. Am I right?
Of course not. I mean, okay, of course you can use a test function, you can use any function. But what I tell you is any function that you get for f0, okay, the derivative because of the Berezin integral put to 0 this part, okay, and then automatically your integration is 0, okay.
Okay.
Independently of f naught.
Yes, yes, I agree.
I think that I did like 1% of what I want to discuss.
No, but Antonio, if we can abuse your time, I think I would love to hear more on this next time. But I mean, I prefer to, I mean, personally, I prefer to go slow. I don't know about the rest of the audience. If they're bored, I could just meet with you.
Well, I don't know. I mean, I can do a third, let's say, a third part, but
I would definitely enjoy it, but it depends on who else would enjoy, who is there, the victims. Mariana had to leave, but I'm sure she will like it. But how about the rest?
Well, what would be the topics?
Well, the topics would be picture changing operators. Actually, here I didn't even scratch this topic, which is actually very important because allows you to convert a superform into integral forms. Okay.
Yeah, that is exciting.
So
Yes.
it gives you a very rich structure of the complex of superforms in integral form because are operators which allows to go from one complex to the other complex. And those operators are very, let's say, very nice indeed, actually, because are kind of very deep constructions. Okay.
So what do you say, John?
No, I think it's good. I think you should continue. I have to leave now though.
Yeah, okay. Maybe we should. I will stop the recording because I think, Antonio, if everyone is leaving, maybe we should keep going.
No, of course, that's fine for me. Yes, I'm completely tired.
Look,
now.
Emanuele said the third part would be great.